So, good morning everyone. Today we will discuss about kinetic and potential energy. So, if we talk about kinetic energy, as earlier we had discussed that energy and work, they are just two faces of the same coin. So, you can transform work into energy as well as energy into work done. Now, what is actually kinetic energy? If we talk about a standard definition, for a standard definition, please you need to pay attention. We always need to do some work against a force. We know it very well. Work is always done against a force. Work is always done against a force. During the conservative forces, we have discussed this particular line. Work is always done against a force. So, definitely, the amount of work which is done, or the work which is done to bring a body from a state of rest to the state of constant motion or uniform motion, to the state of constant or uniform motion, that amount of work is called kinetic energy of the body. Yeah, we can say that amount of work will be stored in the form of kinetic energy in the body. So you need to pay attention on this thing. It is the amount of work which is done to bring a body from the state of rest to the state of uniform motion or constant motion. This thing you need to pay attention. This is the basic idea of blueprint of derivation for kinetic energy. So we can derive the expression in two ways: general analytical method or mathematical method, or second is calculus method. So let's pay attention on this definition and let's try to implement this definition for this particular case, that a body initially is at rest 0 and you have done some work over it by applying a force F, due to which now the velocity body's velocity becomes v and it is trying to move with this constant velocity. You need to keep this velocity constant. So we need to do some work over it, and we know that the work done W equals to Fs cos theta. We know it very well, where S is displacement from A to B, that is S, the displacement, and work done is Fs cos theta. Since the displacement and force, they are in the same direction, so you can say theta is 0 or cos 0 is plus 1. So the work done is F into S simply, because cos 0 is plus 1. Or you can say work done is mass into acceleration into displacement. Now you have two choices. Either you can replace acceleration or you can replace displacement. It's your choice. From third equation of motion, v square equals to u square plus 2as. We know it very well. So a would be v square minus u square upon 2s. You can put this value of acceleration in this expression. So work done, so you can say work done W equals to m into v square minus u square upon 2s into s. S to s will get cancelled, or you can say W equals to, now you need to pay attention on this, half mv square minus half mu square over this basic idea. But right now I'm not talking about this particular expression, I'm just highlighting it. Let's say equation first. Since we are talking about a very specific case in which body initially must be at rest, please pay attention. Only in that particular case you can call it kinetic energy, when the body is we can say is being brought from state of rest to state of motion, not from motion to motion or motion to rest, from the state of rest to state of motion. So definitely, if you are saying if u is 0, in that particular case W is called kinetic energy, capital K. So if you are placing u as 0, at that time you will be capable to replace W by capital K. So equation first would become equation first would become capital K equals to half mv square only. That is the formula for kinetic energy for a body which is moving with v velocity. A body of mass m which is moving with a constant velocity v, its kinetic energy would be half mv square. This is a general method to derive the formula. Another way is the calculus form, and which is actually very easy. The same definition will be applied for the calculus form, but with a small change. With a small change, you need to pay attention. In the calculus form, or you can say calculus method, we will take the work done for a very small displacement dx. For this small displacement dx, there will be a small amount of work. So dw is the small work for the small displacement dx. And the same method we had discussed during the introduction to calculus method. So dw would be f into dx. Theta again 0, since theta is 0, so cos 0 is plus 1. Integrating both sides. So you will get dw 0 to k. If, now please pay attention that either you will have to replace dx or now let's first solve it, simplify. Mass into acceleration into dx. You can write like this, mass into acceleration into dx. Now you have a choice to replace acceleration or to replace dx. So we can do one thing, we know it very well. Acceleration is dv by dt, change in velocity with respect to time. You can put it here. So this expression will turn into dw equals to m into dv by dt into dx, like this. And now if we swap the denominator, read it like this, dx upon dt. So we know it very well, velocity is change in position with respect to time, dx upon dt. So we can replace, instead of dx upon dt, we can write v. So it will turn dw equals to m into v into dv. Now you can integrate. Don't say it a dv square. V is the instantaneous velocity, dv is the respective term by which it is differentiated or integrated. So integrating both sides, and if you are placing the limit u as 0, at that time you can put the limit of work done as capital K, kinetic energy. 1 dw equals to, mass is a constant, velocity integration with respect to v, 0 to v. Keep this thing in your mind, it will be 0 to v, because initial velocity would be 0 if you are calling it kinetic energy. Initial velocity must be 0. And integration of v, it would be v square by 2, and we can say x to the power n plus 1 upon n plus 1 formula we are putting. So it will become v square by 2 simply. So mv square by 2, or you can say kinetic energy K equals to half mv square. So the same formula you will get either by a calculus method or by a general mathematical method. For the same example, you will be able to derive the formula for kinetic energy. If we are talking about that particular case in which body initially is in motion, actually it is not at rest, in that particular case you can't call it kinetic energy, because the kinetic energy is the amount of work which is done to bring a body at a constant motion from the state of rest, and now it is initially at motion. So you will keep this motion as u square simply, whatever you are talking about, normal method or calculus method. So in the calculus method, you will integrate it from u to v. Do not put 0, u to v. So it is simply called the work done, 0 to w, work done. And now integration is v square by 2 and upper limit minus lower limit. So it will turn into one interesting outcome, that is m into v square by 2 minus m into u square by 2. You can write like this. Or we know it very well, half mv square is the kinetic energy. You can continue up to this level, equation first. So whatever you are going through the calculus method or you are going through the analytical method, work done would be, w would be half mv square minus half mu square. Still you will reach on the same point, that work done would be half mv square minus half mu square. And half mv square is the kinetic energy at point B, means final kinetic energy, and half mu square means initial kinetic energy. So definitely it will give you the value of change in kinetic energy. Kinetic energy final minus kinetic energy initial, or you can write work done equals to change in kinetic energy. Means if you are doing some work on a moving body, it will definitely bring a change in its kinetic energy. Work done would be change in kinetic energy. This is the basic conclusion, and this conclusion is called work energy theorem. This conclusion is simply called work energy theorem. So it is a very important topic regarding your examinations. You will get some kind of numeric problem. You might be get some kind of numerical problem based on this, that if that amount of work is being done on a body, then what will the new velocity of the body? So initial velocity would be given. So the mass would be given. So you can go for this formula. Work done will bring a change in kinetic energy. So you can calculate the final velocity even from this formula. So next topic is potential energy. And please pay attention, not every time the formula of potential energy is mgh. No, not every time it is mgh. So the core concept of potential energy is the amount of work which is done to bring a body at a particular position, or to keep a body at a particular position against an opposing force. That amount of work will be stored in the form of potential energy. Means the amount of work, or the work which is done, to bring a body or to keep a body at a particular position to bring a body or to keep a body at a particular position against an opposing force is stored in the body. That amount of work is stored in the body in the form of potential energy. In the form of potential energy. You need to pay attention on this thing. It is very important regarding the derivation. Means if you are keeping a body at the state of rest, or you are bringing a body at a particular position even still in the state of rest, the amount of work which is done against the force is stored in the body in the form of potential energy. Means, for an example, you are holding this marker at a particular height, against the gravitational force, you are keeping it at rest. Still you will feel some kind of tiredness after some time. Why? Because you are transforming your body biochemical energy directly into the gravitational potential energy. In the same way, if you are trying to keep a spring compressed, you are still working against the restoring force of the we can say spring, and that amount of work will be stored in the form of potential energy in the compressed spring. So it is not necessary that every time potential energy formula is mgh. It depends totally on the opposing force. Means the name of potential energy or the type of potential energy will be decided by the opposing force against which you are actually doing some work. So if you are we can say, if the opposing force is gravity, against which you are keeping a body at rest or you are bringing a body at a particular position. So opposing force, if it is gravitational force, in that situation potential energy will be called gravitational potential energy. Gravitational potential energy. You can say, if that opposing force is electric force, means against the electric force you are keeping or you are bringing a body at a particular position, so that potential energy will be called electric potential energy. If you are keeping a body, we can say, if you are bringing a body against elastic force or restoring force, you can say elastic force. The work done against this force, it will be called elastic potential energy. Elastic potential energy. So it's totally depends on the nature of opposing force. and that will be the root cause of the development of potential energy in a body. Now let's prove that not every time potential energy formula is mgh. So right now I am trying to derive the potential energy for a compressed spring. Potential energy is stored in a compressed spring which is placed horizontally like this. So this is the normal, on a frictionless surface, normal state of a spring, not compressed, and this is a normal state. And now you are displacing it or you are compressing it against its restoring force. Whatever you are expanding it or compressing it, you have to do some work against its restoring or elastic force, you can say. So you are applying a force over it. Suppose we are compressing it and you have displaced it with a displacement of, let's say, x. This is the compressed state, and you have displaced it from this position to this position. This is the total displacement x, and obviously you have to do some work because it is still applying a force in opposite direction, that is restoring force, Fr. Fr is restoring force of the spring, restoring force. So you have to do some work against this force, and it is a dynamic force, it is not a static force. You need to pay attention, it is not the static force, it is a dynamic. Dynamic means its value will depend on the level of compression or expansion. It is a dynamic force, dynamic or variable in nature. You can say dynamic or variable. It is not a constant force, it is a variable force. And this is the theme of the derivation, that if it is a variable force, so definitely you have to apply a variable force against it to keep a body at position of rest. If the body is at rest, definitely applied force is equal and opposite to the restoring force, definitely. So you need to pay attention, it is a variable force, means the restoring force is directly proportional to the level of compression or expansion. Why? Greater you expand or compress the spring, greater you will experience the restoring force. So restoring force is directly proportional to x and in negative sign because it is in the opposite direction. Negative due to the opposite direction. Restoring force always act in the opposite direction to the level of compression or expansion. If you are compressing it in this way, you are compressing it, so definitely it will act in the outward direction, and if you are extending the spring, it will act in the inward direction, so opposite to it. Or you can write Fr equals to K constant minus Kx, where K is called spring constant or restoration constant. It is called some spring constant for this particular spring. Spring constant, or you can call it compression or expansion factor. So spring constant, we will name it simple, spring constant. So it is definitely a variable force which depends on x. So for an example, I would just like to find out the potential energy stored in this. So I can do one thing, that suppose this spring has been compressed by a small displacement dx. By a small displacement dx compression level. For this small compression, for, you can say, a small compression or expansion, compression dx, a small work will be done. A small work dw is done. So definitely this work would be dw equals to f dx cos theta. You can see clearly f dx cos theta, and if you are replacing f by fr, so definitely the angle would be 180. That's why minus is there. That's why minus is there. So it's your choice completely. So you can write minus fr dx because theta is 180 for fr and x. Keep this thing on. If you want to replace f by fr, so definitely you have to take theta as 180. So minus fr dx because cos 180 is minus 1. And now you can place the value of fr, which is actually minus kx. So you can write, or dw equals to minus kx small k x into dx. Now integrating both sides again, integration, and the work done to keep a body at rest against the restoring force, it will be called the potential energy, which is represented by capital U. Potential energy is represented by capital U. So 0 to capital U, 1 integration with respect to work done dw, and minus k is a constant integration of x with respect to x, 0 to x integration. So obviously you will get u equals to integration of 1 is w and limit is u minus 0, that is u. U equals to x integration with respect to x, it would be x square by 2. So it is minus half k x square. This is the potential energy stored in a compressed spring. This is the expression for potential energy stored in a compressed spring, and this is not actually mgh. So not every time the potential energy formula is mgh. Mgh is the gravitational potential energy, which you can derive easily, that the work done to hold a body against gravity at height h of mass m. So its weight would be mg acting downward. So you have to apply a force equal to weight F and height is h. So force into displacement. Force is mg and height is h. So F into s. So mgh. So that is gravitational potential energy. And this is elastic potential energy stored in a compressed spring. So potential energy formula differ for every opposing force. It is not a constant. Keep this thing in your mind.